Hi, my name is Subramonyam, and I'm a PhD candidate at the University of Michigan School of Information. Today, I'm going to talk to you about our CHI 2020 paper called texSketch, Active Diagramming through Pen-and-Ink Annotations. This work is in collaboration with Colleen Seifert and Priti Shah from the Department of Psychology here at U of M and Eytan Adar from UMSI. It is finally springtime in the United States, and then this happens. Parts of the US are experiencing really low temperatures and snowfall because of a polar vortex. And last year, there were a lot of discussions around whether or not these recurring events are associated with global warming. Well, do we know what a polar vortex is? And can we reason about the associations between global warming and the weakening of the polar vortex? It is a complex network of causal relationships. To understand this argument, we need to first acquire a mental model of how a polar vortex is formed. Then we need to understand why it typically remains confined to the poles. Building on this understanding, we need to infer the causal relationships between warmer temperatures and the weakening of the polar vortex, which causes a cold snap here in the US. How do we develop this understanding? Well, text remains the primary medium for science communication, and we need to build this understanding from reading text. According to theories of text comprehension, learning from text is a constructive process. Consider this first sentence of the polar vortex article. As you read it, you need to identify and recruit individual concepts into your working memory. Then, you need to build sentence-level associations between those concepts, in this case, causal associations. As you read further along, you do the same thing for the subsequent sentences and finally integrate propositions across different sentences into a coherent mental model. But for many readers, building these associations in the mind can be challenging. Science text often includes difficult and unfamiliar vocabulary. The text structure can be complex and include generalized descriptions as well as specific instantiations that the readers need to connect and make inferences about. And finally, readers may be limited in their working memory and attention that may result in a fragmented understanding of the text. Knowledge externalization strategies such as highlighting and note-taking allow readers to record their thought processes using persistent and manipulable representations. For instance, by highlighting and underlining the text, readers are able to externally select or emphasize key concepts for building associations. Through list structures, they can organize the annotations into meaningful associations. Finally, diagramming allows them to integrate those associations into a coherent mental model. But the problem is readers often have to switch between different tools for reading, note-taking, and diagramming, which can be disruptive. Reading complex text requires iterations and seamless switching between different levels of representation. Active reading tools such as this one emphasize sentence-level annotations, but note-taking and diagramming are secondary and disconnected. On the other hand, diagramming tools emphasize the drawing canvas, limiting the usefulness of annotations on the text display for diagram construction. In fact, studies have shown that while diagramming is useful for comprehension, the effort required to make diagrams often outweigh its benefits. Tools such as liquid text and margin notes support both text and canvas as a side-by-side layout, but the different levels of representations are still largely disconnected. Ideally, reading tools should allow low-level representations to be merged upwards to build integrated mental models. Our main motivation for this work is to investigate how we can facilitate externalization across different levels of understanding without burdening the reader. Our approach is to look at ways to link active reading and diagramming tasks, a generative learning strategy that we call active diagramming. In the rest of this presentation, I will describe a design probe study that we conducted to explore active diagramming, then talk about texSketch, our tool for active diagramming, and finally the evaluation of texSketch. For the probe study, we selected 4 different science texts about rain, lightning, car engine, and coral bleaching. Each has a reading time of approximately 1 minute, and all are causal explanations because a majority of science text is causal in nature, and students find it hard to understand causal relationships. We recruited 5 participants with experience in visual note-taking, and we asked them to read the text and construct causal diagrams from the explanations. We used an ABA study protocol in which participants first used pen and paper for the text about rain. Then they used the baseline version of texSketch, which implemented features similar to liquid text using pen and ink interactions. Finally, they returned to the paper condition for the text about coral bleaching. Our goal was to understand how readers might produce diagrams on pen and paper, elicit feature requirements for the tool, and finally allow participants to reflect on the differences between the tool and paper conditions to provide comparative feedback. We coded the video recordings for different diagramming activities, we analyzed the diagram for correctness and completeness, and elicited participants' feedback through an informal retrospective interview. A key finding was that 4 out of 5 participants produced fragmented diagrams in both conditions. In other words, the diagrams were not coherent and only represented sentence-level associations. Second, in the paper condition, participants took between 5 to 10 minutes to read the text and make diagrams from each text. The main driver for this is that it took roughly 10 seconds to create a single node in the causal diagram. Third, we noticed that participants were constantly switching between reading and diagramming tasks. Each time they identified a concept, they switched from reading to creating a node for that concept. As reported by our participants, my goal was to make the diagram rather than to really understand the material, and I'm unsure if doing it at this low level was as effective. While it is necessary to switch between reading and diagramming tasks, frequent switching can be ineffective. Based on these findings, we derived a set of design guidelines for active diagramming, and I refer you to the paper for details about this. A key interaction paradigm in texSketch is that we can combine text with ink annotations to automatically generate diagram representations. That is, text plus ink annotation equals glyph. And a second key paradigm is that we can use natural language processing to scaffold the reading and diagramming tasks. Combining these two paradigms gives us a rich design space for active diagramming, including text semantics, annotation attributes such as shape of the glyph, tool type, color and stroke thickness, and annotation sequence, all of which can be mapped to different diagramming tasks. The interface for texSketch consists of a text view on the left and a diagram view on the right. The text view also includes pen and highlighter tools and page navigation controls for multi-page text. The diagram view has a set of controls for setting diagram type, undo, delete, review, and diagram rotation. As an example, let us look at how texSketch can support causal diagramming. In our AD workflow, we encourage a 2-pass reading approach. A first pre-reading pass to highlight important sentences and then engage in focused reading. As the user highlights the text, texSketch identifies potential causal phrases in that text. This is presented as underlined hints. Then in the second pass, the reader can revisit the highlighted text and select causal concepts. Underlining a word or phrase will automatically add it to the diagram view. After adding a few concepts, readers can make associations between them by drawing a line across different concepts. They can do this from the text or the diagram view. Our design supports a deferred action approach in which readers can add multiple concepts and later delete redundant or unwanted concepts. They can delete nodes and links from the text or the diagram view. To organize different associations, texSketch supports creating subdiagrams through annotation gestures. Readers can integrate different subdiagrams by linking them in the diagram view. In this manner, the reader can construct coherent causal models from raw text. In addition to structured diagramming, our NLP annotation features allow for unconstrained visual note-taking. In this example, underlining a text adds it as a node in the diagram view, but underlining it a second time creates an icon representation. We use the Noun Project API to search for icons. Readers can also define their own glyphs for individual word or phrases. In this case, the reader is defining what they want the engine to look like in their diagram. And then underlining that word a second time will use that same glyph for the word engine. Once the diagram is completed, readers can use it as a visual table of content to reread the text at a later time. Hovering over a node with the pen tool highlights the corresponding text in the text view. Readers can also review their understanding by recreating the links in the diagram view from memory. To briefly go over the architecture, each diagram type in texSketch consists of three main modules. The first is the Annotation Processing module, which consists of a dictionary of mapping between annotations and diagram functions. It also includes a stroke recognizer to identify the pen annotation. The second module is the Text Processing module, which includes functionality for text extraction and NLP processing. The third is the Diagram Specification module, which generates SVG code for what the diagram output should look like. When the user inputs an annotation, the Annotation Processing module identifies the right function to execute, the Text Extraction module fetches the text associated with that annotation, and the diagram generator invokes that function using the associated text to generate SVG code. The code is then rendered onto the diagram view by the SVG rendering module. For complete details about our architecture, we refer you to our paper. To evaluate texSketch, we use the same tasks from the probe study. The first two texts were used as practice, and then we tested participants using the text about lightning and coral bleaching. We recruited 12 participants for the study with prior experience in visual note-taking. We provided them with a brief tutorial of texSketch, and then they engaged in the practice and the test task. After each task, they filled out a cognitive load survey. Finally, they responded to a usability questionnaire and participated in informal feedback. As you can see from the log data, all but one participant followed a two-pass reading approach. In the second pass, a few of our participants started with the final effect and then backtracked their way to the initial cause. The low cost to create and delete diagram elements, along with the sketchy look and feel, encouraged a drafting approach to comprehension as opposed to deliberate creation or crafting. The cognitive load questionnaire measures the intrinsic load, which is the difficulty of the content, the extraneous load from using the tool intervention, and germane load, which is readers' self-perceived learning. As we can see, participants reported fairly low on extraneous load from using the tool. Unlike the probe study, 11 out of 12 participants produced a single coherent diagram for the explanation. By evaluating the diagram against a rubric, they produced 83% correct notes for lightning and 90% correct notes for coral bleaching, and 78% correct links for lightning and 93% correct links for coral bleaching. We also noticed that participants had additional notes that indicated link descriptions. Lastly, participants expressed that they wished they had a tool like texSketch when in high school and also appreciated our annotation to diagram features. However, they had mixed opinions about the usefulness of NLP hints. This may be in part due to the limitation of the NLP models we used that were not very accurate, but also it could be the simplicity of the text. We are currently investigating the NLP features for trade-offs between accuracy and usefulness, and also evaluating the learning benefits from using texSketch in comparison to other approaches. In summary, reading is a constructive process of selection, organization, and integration. External aids are useful, but current tools don't lend themselves well to different levels of representation. Active diagramming and texSketch provides flexibility when reading and diagramming, which reduces non-desirable and distracting difficulties. And finally, our architecture and interaction mechanism of text plus annotation equals glyph can be applied to many different diagram types. Thanks for watching.